In this video, we're going to talk about section 4.5. This is going to be the first of two parts about this section. We're going to be focusing on the first derivative and how it impacts the shape of a graph. And then in part two, we'll talk about the second derivative and how that impacts shape of the graph. Okay, so let's start by just doing an example. We want to know where is the function f of x equals x to the fourth minus 8x squared plus 3 increasing, and where is it decreasing? So first of all, an increasing function is one that's going up if you read it from left to right. A decreasing function is one that's going down, again, if you read it from left to right. Increasing functions have positive slopes. So that means the derivative is positive if the graph is increasing, and the derivative would be negative, or you have negative slopes, if the function is decreasing. So how do we determine where a function is increasing or decreasing? Well, we're going to analyze the sign, whether it's positive or negative, of the first derivative. And so I have the steps written out on this slide, and then we'll come back to that example. But if you look to the left, I have a picture. You can see increasing is where the graph is going up, decreasing is where it's going down. So positive slopes versus negative slopes. The thing to really notice when you're looking at that picture is a graph can only change from increasing to decreasing at a critical point. So that would be a place where you have a horizontal tangent line, or it would be possible to have a sharp point or an asymptote, places where the derivative doesn't exist. Also could be places where the function changes from increasing to decreasing. So first thing we're going to do is we're going to find all critical points. We did that, I think it was a couple sections ago, but critical points are basically places where the derivative is 0, or where the derivative doesn't exist, right? So we're trying to find these transition points, these places where we have horizontal tangent lines, sharp points, or asymptotes. Once we find our critical points, we're going to create a table using those critical numbers, and I'll show you exactly what I mean by that in our next example. But basically, I'm missing something here. I put my critical numbers on a number line. So basically, I just take like a number line and I mark it with my critical numbers, and I use that to create a table. And then I pick test intervals in each region of that number line to analyze the sign of my derivative. Oh, I'm missing a lot on this slide. Sorry. That's what I get for trying to write all the steps out. All right, so we'll use test values to analyze the sign of our derivative in each interval. If that derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. Okay, so let's go back to that problem and see if we can follow these 4 steps. And perhaps I can explain a little better what I mean by these 4 steps when we take a look at a specific example. So here's the problem we're trying to do. Where is the function increasing? Where is the function decreasing? So the very first thing I'm going to do is find the derivative. And that's what I've done in that first line. So I found the derivative. I got 4x to the third minus 16x. Step 1 is find those critical points. So that means set the derivative equal to 0. So I set this derivative equal to 0 and decided to solve by factoring. There's a GCF, or a greatest common factor, of 4x. So I took the 4x out and left with x squared minus 4. And then that's a difference of perfect squares. It becomes x plus 2, x minus 2. I set each factor equal to 0. So I have 3 critical numbers, 0, -2, and 2. Okay, so that was step 1. We find the derivative. We set it equal to 0. if we have a fraction as our derivative, we're going to have to set the bottom equal to 0 as well, because we do want to think about where is that derivative undefined. Okay, step 2 is make a table. And so what I've done here is I just drew a number line. And then in red, I have placed my critical numbers on my number line. So I have critical numbers of -2, 0, and 2. So that was step 2. I create a table on the number line using my critical numbers. Step 3, we're going to pick test values in each of the intervals, each of the regions that I've divided the number line into. And so my test values I have written in blue here. So this -3 is a test value. But really, you could pick any number from -infinity to -2. So the goal is you pick any number on this interval. So any number smaller than -2, I decided to pick -3. And then for my second test value, you can pick any number between -2 and 0. I chose -1. Any number between 0 and 2, I chose 1. And finally, any number that's larger than 2, I chose 3. So those are my test values. So I pick test values in each of these intervals. And the goal is to figure out, is the derivative positive or negative? So the next thing we're going to do is we're going to take these test values and we're going to plug them into our derivative. Okay, so I started by plugging -3 into that derivative, and feel free to put this into your calculator. And I ended up getting -60. Now, the important information, really the only information I care about, is that number is negative. So I put little negative signs in my table to remember the derivative is negative in this region. I'm going to do the same thing for my other test values. So I'm going to take -1, plug that into my derivative. I'm going to plug in +1, and I'm going to plug in +3. And so I didn't show my work, I just used my calculator for these. I put each of these x values, again, into that first derivative, into my derivative. And then in the table, I really just want to keep track of the sign, whether the answer was positive or negative. So when I plugged -1 in, I got 12, that's a positive. So I put plus signs. And then in the next interval, when I put 1 in, I got -12, so negatives. And then finally, when I plugged 3 in, I got 60, a positive number. So I put in those plus signs. So all of this work was step 3. I used test values. I plugged them into my derivative to figure out where's the derivative positive or negative. And then finally, we can just look at our table to answer the question. The function is going to be increasing anywhere you see plus signs and decreasing anywhere you see the minus signs. So I would say this function is decreasing from -infinity to -2 and from 0 to 2. The function would be increasing from -2 to 0 or 2 to infinity. All right, so that's my process for determining where a function is increasing and where it is decreasing. Let's do another example. This one's got a trig function in it, but we're going to do the same process. Where is the function 2 tan x minus tangent squared x increasing? Where is it decreasing? And they're telling us we can just look at the interval from 0 to 2 pi. So we don't have to worry about all numbers or all those coterminal angles. So step 1, find all critical numbers. So I have to find the derivative. The derivative of tangent x is secant squared x. So that's how I got the 2 secant squared x. And then for the second term, I had to use the chain rule on that. So I brought the 2 down, 2 tan x, and then the derivative of tan x is secant squared. It's my outside times my inside derivative. Now I'm going to set this thing equal to 0, and we can factor out both a 2 and a secant squared. Pull out both the 2 and the secant squared, and then we're left with a 1 minus tan x. Now I'm going to set each of those factors equal to 0. So we have to figure out, when does secant squared equal 0? When does 1 minus tan x equal 0? Well, secant squared is the same thing as 1 over cosine squared. And the only way a fraction can equal 0 is if the numerator equals 0. 1 will never equal 0. And so secant squared is never going to equal 0. All right, but what about the 1 minus tan x? Well, we could isolate the trig function. So you could minus the 1 and then divide by negative 1. You end up getting tan x equals 1. And then you got to think about your unit circle. Where on the unit circle is tangent positive 1? That would be my 45-degree angle. So that's how I got the pi over 4. But tangent is also positive in quadrant 3. And so that would be the 5 pi over 4. So my derivative is 0 at pi over 4 and 5 pi over 4. Those are critical numbers that will have to go on my table. Now I also need to think about, are there places where my derivative does not exist? And so to do that, I'm going to set denominators equal to 0. And so we have a secant and a tangent in this problem. We have both secants and tangents. Both of those trig functions have denominators that are cosine x. Right? So secant is 1 over cosine, tangent is sine over cosine. Both of those trig functions have denominators of cosine x. So both the function and the derivative are undefined when cosine x equals 0. Right? So we have to set the denominator equal to 0. When does cosine x equal 0? Again, I think about my unit circle. When do we have an x-coordinate of 0? That would be my 90-degree angle, so pi over 2, or the 3 pi over 2 as well. So in my table, I'm going to have to include the pi over 4, the 5 pi over 4, the pi over 2, and the 3 pi over 2. All right, so that's step 2. And make sure you actually list these numbers from smallest to largest. You have to list them in order. So the 45-degree angle was the smallest, then the 90-degree, then the 5 pi over 4, and then 3 pi over 2. So I've divided my number line, which really only needs to go from 0 to 2 pi, using all these critical numbers that I found. That was step 2. Step 3, I'm going to pick a test value in each of these regions. I'm going to take that test value and I'm going to plug it into my derivative. So for example, something that's between 0 and pi over 4 would be pi over 6. If it helps, you are more than welcome to change this into degrees and put your calculator in degree mode, if that helps you pick your test values. You could also, because you're using a calculator, you're welcome to convert all these angles into decimals so you could figure out what is pi divided by 4. You could just type that into your calculator. It's like 0.785. So then something smaller than that would be 0.5. So you can work with decimals if that's easier as well. I chose pi over 6. I plugged that into my derivative. Because I'm using pi over 6, I had to make sure I was in radian mode. And again, for the secants, my calculator doesn't have a button for secant, so I have to enter 1 over cosine for those secants. I ended up getting a positive number, and so that's why I put that plus sign into my table. And then I went through and I picked test values in each of the other regions. I didn't write down what they were, but if I was picking something between pi over 4 and pi over 2, I might pick pi over 3, or 60 degrees. And when I put that into my calculator, I got a negative. And then I picked something between pi over 2 and 5 pi over 4. I think 7 pi over 6 works. And then I picked something between 5 pi over 4 and 3 pi over 2. 4 pi over 3 maybe. And then something between 3 pi over 4 and 2 pi. You do like 7 pi over 4. Again, I know it takes a lot of thought to work with these fractional pi's, so feel free to work with degrees or decimals. But I filled out my table where I have the plus signs, the function is increasing, and where I have the minus signs, the function is decreasing. So we can say that this function is increasing from 0 to pi over 4, pi over 2 to 5 pi over 4, and 3 pi over 2 to 2 pi, and then it's decreasing from pi over 4 to pi over 2, and 5 pi over 4 to 3 pi over 2. All right, let's extend this process a little bit. For my next example, it says find all relative extrema of the function. And so now we want to indicate where are those peaks and valleys, where are those high points and low points. So to answer this question, we are going to use the exact same process. We're going to find our critical numbers, make a table, use test values to analyze the sign of the first derivative. But we're really going to take this one step further. We're going to indicate that if you have plus signs and then minus signs, that means your derivative is positive and then negative. So your function would be increasing and then decreasing. That means you have to have a max. If the critical number is a place where the function transitions from decreasing to increasing, it has to be a min. This process, this thought process of making a table and using the increasing and decreasing information to pick out your local maxes and mins is sometimes called the first derivative test. And so that's what we'll be doing, using the first derivative test to find maxes and mins. Okay, so same steps as before, we're just taking it one step further. So I'm going to find my derivative. I got 6x squared minus 30x. I'm going to set it equal to 0 to find those critical numbers. So I factored out a 6x. I'm left with x minus 5. Set the factors equal to 0. So 0 and 5 are my critical numbers. So that was step 1. Step 2, I'm going to create a table using those critical numbers 0 and 5. Then I'm going to pick test values. I picked -1 as something that's smaller than 0. +1 is between 0 and 5. And 6 is something that's bigger than 5. Then I'm going to take those test values, I plug them into my derivative. When I plugged -1 in, I ended up getting +36, so I put a plus sign in my table. I do the same for the 1 and the 6. When I put 1 in, I think I got negative 24, so I put the negative in. And then when I put 6 in, I got positive 36 again, so I put that plus sign in the table. So this table tells me the function is increasing, then decreasing, then increasing. Plus signs mean increasing, minus signs mean decreasing. That tells me that 0 has to be a max and 5 has to be a min. You can, if you draw the arrows, you can actually kind of see that 0 would be your high point, 5 would be your low point. We're going to write these answers as ordered pairs. So when you give me a max or a min, you're going to write both the x and the y coordinate of that point. That's an actual point on the graph. So I have a max at x equals 0, I have a min at x equals 5. To find the y value, you're going to take those numbers and you're going to plug them into that original function, which I have circled in yellow. So if I plug 0 into f of x, I get 6. That's my y value. If I plug 5 in, I use my calculator for that. I got negative 119. So that's my y value at 5. So we have a local min at 5, negative 119. All right, my next example is a little bit different, more of a thinking problem. So in this problem, we're given the graph of the derivative of a function. So what I have graphed is y equals g prime of x. So again, this is not function g, this is a graph of its derivative. And so what's been plotted on the y-axis here are actually slopes. The slopes are all graphed. Based on the graph of the derivative, we are going to try to determine where is the original function g increasing and where is the original function decreasing. And then we'll answer the question, does that function have any local maxes or mins? All right, so we know that functions are increasing where the derivative is positive. And so to help me answer this question, I'm going to take the information that's given to me in this graph, and I'm going to translate that into a number line, just like what we've been doing in the previous problems. So again, the thing that's been graphed is not the original function, it is the derivative, right? So the derivative has been graphed, and I can see that from negative infinity until I get to 2, this region has negative y values. The y values in this region, which represent the derivative, are all negative. And so that's why I put negatives in my table. Then from 2 to 4, all of a sudden now the curve has positive y values. Okay, it's above the x-axis. These y values are positive. Again, the y values represent the derivative, so I put plus signs in my table. And then we're back to negative y values again once we go past 4, so I put negatives in my table. So this part has negative y values. So then to answer the question, where is the function increasing? I can just look at my number line. It's increasing where I see the plus signs. So that would be from 2 to 4. And it's decreasing where I see the minus signs, which would be from negative infinity to 2 and 4 to infinity. I think drawing the number line really helps in these problems because it's hard to switch your brain from thinking about, I'm looking at the graph of a derivative versus a graph of the original function, right? Because if we're just looking at the original function, we look at where is it going up versus down. When we look at a graph of the derivative, we're looking for positive y values versus negative y values. And then does this function have any local extrema? Where, again, I'm going to look at my table. I'm going to look at my number line to answer this. I can see it goes from decreasing to increasing at 2. So that means I have a min at 2. And then I must have a max at 4. I don't have any way of finding the y values because they didn't actually tell us what the equation was. So all we can say is min at 2, max at 4. All right, that's it for part 1 of section 4.5. I've got a very quick summary on this last slide. The derivative, or first derivative, tells us whether a function is increasing or decreasing, and we can use this information to find maxes and mins. I'll stop here in this video, but we'll continue with this section by thinking about what is the second derivative going to tell us about graphs of functions.